Hello my dear, I welcome you all in this second session of fluid mechanics. So in this session we will discuss the continuity of the previous session, that means viscous shear stress, and the viscous shear stress of part 2 we will discuss. Okay, so please reply in the comment whether audio and video clear or not, please everyone. Okay, I think all set. Okay, all set. So my dear, what is the motivation, what is the motive of today's class? The motive of today's class, matlab what we have to learn after this finishing of this class, what we have to learn. See, previously we have to discuss that one of the law, that is a Newton's law of viscosity, and also we have to discuss the property, one of the best property known as viscosity, that play a very important role while regarding, okay, thank you Matan, while regarding the fluid will flow. Okay, so viscous stresses part 2 will discuss the common engineering model, and that common engineering model is your court flow. So we already know that if you think about that, okay, sir, what is the practical application of the court flow? There are a very huge application. What is that? So commonly they are used in ball bearing. So there is a bearing, ball bearing is there, in that there is a fluid is there. So that fluid, if you analyze the viscosity or power loss during that motion of the bearing, we calculate, we have information of that shear stress. That means we have to know the shear stress, viscous shear stress, so that we can calculate how much the power will be consumed, how much the power will required to run that bearing while present the viscous fluid. So that is the one part, that is also a court flow model. While you design the tire of the any vehicles, so while you design the tire, that means you design the grooves on the tire. So in that one, we also the model as a court flow. That one will decide. There is a hydroplaning concept. In that one, there is a plane of hydroplaning, and that also will be discussed. Already discussed. That is the model of court flow. Also, in the core mantle, that earth, inside the earth, there is a core and mantle is there. So for that analysis, we also do the court flow analysis, atmospheric analysis. Atmospheric have a different layers. So if you analyze the layer of the atmosphere, that also will apply the court flow. So court flow have a very common and very simple models of fluid mechanics. My dear, sometimes some student will ask me, they confuse that, sir, during the court flow whether the pressure is constant or not. See, it's your hand. You may be take a pressure constant, you will not be take a pressure constant. Why? Because fluid will ultimately flow, and flow is due to the mechanism of boundary displacement only, so we can neglect the pressure. So for the simplicity analysis of a court flow, first we have to assume the fluid will flow due to the not present of the pressure difference. That means only the fluid, that means throughout the pressure is constant in the flowing direction. That means their pressure is not varying. So how will the fluid will flow? The fluid will flow due to the displacement of a boundary. So for that one, this is your already we have to discuss that. See, this is the model already. So in that one, we have to design the cars after the braking, how much that the car will travel after applying the locking of the wheel. So for that one, we have to model this. For the calculation of this model, we have to take as a model as a court flow model. So in the court flow model, and there is a hydroplaning. Okay, now, so in generally, how to it will model the court flow. This is the model of the court flow. See, there is a moving plate, and this is your fixed plate. Okay, now there is a fluid in between that. And now, my dear, always remember, you have to take a coordinate, set a coordinate y from the fixed surface to the fluid. So these are the fixed coordinate. Y is the fixed coordinate. It is a fixed. Why it is fixed? That y is always from the fixed surface, fixed solid surface. Okay, so fixed solid surface, we have to take a y. In this direction, you can take x or z. Okay, no problem at all. Now, my dear, the fluid varying, let's suppose the velocity profile within that fluid. Why? Because we are not taking any pressure. That means the fluid will move due to this displacement of a boundary. The fluid will move due to this displacement of a boundary. Now, there is no any pressure difference. There is no any pressure. What is the pressure in upstream? Same pressure is downstream. Only the movement of the fluid is due to the displacement. And also there is a very thin gap. And also very thin gap due to these two mechanisms, due to these two things, the velocity profile is linear. So these are the velocity profile. Now, one thing is that here the particle which is at this point, their velocity, tangential velocity, the tangential velocity of the particles along the motion of the plate, is 0. Why? Because the relative velocity is 0. Why? Because the bottom plate is fixed. That is your no slip condition. Also, the fluid which is at the top of the plate, fluid particles which have a velocity same as the plate velocity, that is also called a no slip boundary condition. My dear, sometimes students get confused. Sir, no slip boundary condition, that means the fluid always, that means they says that sir, fluid at rest. No. In the no slip condition, it is not like that the fluid is rest. Fluid is motion, but the relative motion is 0 along the tangential direction. The relative motion along the tangent direction is 0. That is a no slip condition. It is not like that, sir, no slip condition, that means fluid particle is rest. No, relative velocity is 0 at that point in a flow direction. All the things you have to clear in mind. So this is your now my dear, this is your y direction. That means y direction is perpendicular to that plate. So if you draw the velocity field, if you move that plate, there must be induced a velocity field. Okay. Now, how to define that velocity field? That is important. See, this is your x direction. So we have to take a velocity of this particle, a velocity of any point within the fluid which is in x direction. Now, my dear, one thing is very clear. This is one dimensional flow. Why? Because we are not bothering the flow, it is in y direction or it is in perpendicular to the board. Why? Because, see my dear, how to model this one? How to model that, sir, velocity is only velocity is only x direction? How can you justify you by yourself, sir, the velocity we have to only assume it is in x direction? See my dear, there is no any penetration in the plate. There is no any hole in the plate. That means what is the fluid will there is no any condition to move the fluid perpendicular to the plate in this direction. If there is a punching is there, if there is plate in hole, it may be that the fluid will have a y component. So y component is velocity of a y component is very minimum as compared to velocity in x component. So we have to neglect the y component velocity. Now the plate, this plate is a very wide plate. So this plate is very wide. So the direction of the velocity in the z direction, which is perpendicular to the board, have a very low as compared to the direction in z direction. Why? Because this length is very less as compared to width of the plate. This length is very less as compared to width of the plate, so that what is the movement of the fluid is there, it cannot be crossed in the z direction. Before that it will cross in x direction. So motion in x direction only. So if you write velocity of a fluid particle, so u is the velocity of a fluid particle in which direction? X component of the velocity. So u is the velocity of a particle in x component, and that u will vary. That means if you take fluid particle, this one is 0, there is some velocity, there is some velocity. That means in this direction velocity will vary. So you have to write u is the function of y only. So please mind it, this is the field notation. What the x denotes? The x denotes the component of the velocity. Y denotes the variation of the velocity. So y is the direction in which the velocity will vary. X is the direction where we have to take the velocity in which component. So this is your ux. So my dear, generally we have to write this u is the function of y. Why? Because u by default we are taking a x component velocity. This is your x component of velocity by default. In y direction, v is there. Okay, no problem. Now, what is the profile then? What is the profile? Why we have bothered about that? Why? Because we have to find the shear stress within the plate. Shear stress. From the shear stress, you can easily find the viscous stress. Viscous stress, you have to find the shear stress. That is the kind of viscous stress. Due to that viscous stress, we have to find the viscous force. Once you have to find the viscous force, you can easily calculate what is the power lost during the viscous. What is the power loss when the viscous fluid is present? So you have to design this model. Okay. So this is x velocity component. Now, my dear, see. This is your linear profile. Linear velocity profile. Yes or not? Linear velocity profile. This is your linear velocity profile. Now, my dear, if you apply the linear relationship, that means boundary condition, this is the point where y is equal to 0. The velocity in x direction is 0. Here y is equal to h, the velocity in x direction is your v, and mind it, this is constant. This is constant velocity, very important. This is constant velocity. So all the points is very important here. Now, so if you apply, what is that? Top proportionality, their slope is same, no? So slope is same. This line slope is same. The slope is same. Why? Because this is a linear. So if you apply like that, so if you find du by dy, this is a slope. If you find du by dy, how to find du? That means this is a change. This is your change. Change, that means capital V minus 0 divided by capital H minus 0. So what is that? This du is your V by H into dy. So this is your velocity. This is your velocity. If you integrate it from 0 to h, if you integrate, so this is your y. So what is the variation? If you take the variation, any point, let's suppose this is at a, you have to find this fluid velocity. You have to find this fluid velocity, and this fluid velocity, let's suppose this is what distance at y. So if you integrate du is equal to, this v is constant, h is constant outside, v by h, and you have to integrate from 0 to y dy. So what is your velocity profile? Velocity profile u is equal to v by h into y. Yes or not? V by h into y. So this is your profile, velocity profile. Now, my dear, this velocity profile is a linear. Why? Because it depends upon y. We'll check the boundary condition. If y is equal to 0, velocity at plate on this 0 in the tangential direction is 0. At y is equal to h, velocity is capital V. So that relation is satisfied. So we have to write like that, which velocity? X component of velocity, variation in y direction is equal to plate motion, top plate motion divided by the gap between that into y. So this is your velocity profile. So once you know the field, you can easily understand what is the shear stress. So my dear, if you calculate the tau, now how to denote here? Tau, what is the subscription here? What you have to subscript put here? See, the layer it is in, you have to find the stress between the layer, you have to find the stress between the layer, and what is the direction of that layer? What is the direction? This is, let's suppose this is your layer. Let's suppose this is your layer. This is your layer. So what is the direction of the layer? Y direction. So tau y, and so tau y, it is the direction, matlab it is the direction, and in which direction it will apply? It will apply in x direction. So tau y x. You have to denote like that. So first is the area normal in which the plane is taking, that means normal area, and this is your direction where the force is applied. So you have to apply the force, stress in x direction. So this is x, and you have to apply the shear stress on that area, and that area the normal direction you have to take. So this is your plane. Let's suppose this is your plane. Okay, this is your plane. Okay, my dear. Now you apply the shear stress tau. So what is the direction of this tau? So tau, this is the y direction, beta, and this is your x direction. So tau perpendicular to the plane y, in which direction? X direction. So tau y x. Notation is very important, I am telling you. That is equal to mu dynamic coefficient into du x velocity component divided by dy. So if you put this value here, that is your mu, so y v by h. My dear, see one thing, very important, I am telling you. Tau y x, this one. This was shear stress within that layer. Now, very important, I am telling you. What is the conclusion for that one? This is the shear stress variation in the layer. Now, my dear, mu is constant property, v is your constant velocity, and now h is constant. So, in the chord flow, the shear stress variation is constant. But, my dear, you don't, if and only if there is no any pressure, that means fluid will flow only by the displacement of a boundary. When the fluid is flow only by the displacement of a boundary, in that case the shear stress variation is constant through each and every layer. That means what is the shear stress on this top plate? The same shear stress on the bottom plate. That means if someone asks you what is the ratio of the shear stress from top to bottom, it is 1. The value is 1. Why? Because what is the shear stress at this point? The same shear stress on the lower plate. Why? Because this shear stress variation is constant. That means the ratio between the top and bottom is 1. That is very important, I am telling you. Now, my dear, if this is the calculation, this is the very important part. It is not like that, beta, कि shear stress is always constant. No, shear stress may be 0 within the fluid, shear stress may be varying within the fluid, and shear stress may be constant within the fluid. So this is the first case in which the shear stress is constant through each and every layer. Regardless, the pressure gradient, that means dP over dx is 0. There is no any pressure gradient. That means the fluid flow only due to the displacement of a boundary. So we can write here, my dear, here, what we have to write here? That means we have to write here, fluid will flow only due to displacement of boundary. That means the fluid will flow only the displacement of boundary. There is no any pressure gradient. In that case, the shear stress variation from the bottom layer to top layer or top layer to bottom layer is constant. But it is not always, sir, when the fluid is flowing, the shear stress constant. No, it may be vary. It may be 0. In which case it is 0, beta? Please tell me. In which case it is 0? Everyone, anyone comment? In which case the shear stress variation is 0? Please tell me. In which case the shear stress is 0? Please tell me, beta. Anyone, if you have a knowledge, please tell me. In which case the shear stress is 0? When the flow is uniform. When the flow is uniform, that means there is no any velocity gradient. if there is no any velocity gradient, see, now, think the direction. That slide is very important. Again, I am telling you. That slide is very important. I am telling you, never you have to find in anywhere of this slide. King Kohli, good evening, beta. Never you have. The direction. What is the direction of this shear stress? What is the direction of this shear stress, my dear? What is the direction of this shear stress? See, my dear. What is the direction of this shear stress? See. Okay. What is the direction? See. Please, I am requesting you, be careful. Please, attentive. It is not, it is very easy, but if you not understand, the very difficult. Okay. See, as usual, this is a top plate which is moving. Clear? And this is your bottom place fixed. Okay. Okay. Now, we have to take two chunk of the fluid. Yes or not? We have to take two chunk of the fluid. This one. Let's suppose this is fluid which is near to the top surface, and this fluid which is near to the bottom surface. Please listen very carefully, I am telling you. Please listen very carefully, I am telling you, beta. I am telling you. This fluid element which is nearer to the moving plate, and this fluid element which is nearer to the top plate, bottom plate. Now, if the plate is moving in the right side direction, yes, it is in X direction. I am requesting you, please listen very carefully, I am telling you. Major of this teacher also get confused here. If the plate is moving in a right side direction, so on the plate, the fluid will exert left side shear stress. Left side shear stress. Newton's third law, if the forces on this plate, it is in left side, so on the fluid element, it is in right side. Clear? Now, very important. If you take a very thin layer, very important, I am telling you. If you take a very thin layer in between this, if you take a very thin layer, my dear, please listen very carefully. If you take a very thin layer in between that, if you take a very thin layer, in between that, let's suppose very thin layer. Now, so my dear, please tell me, if we have, so this fluid element, this is our fluid element, and this shear stress on the right side. So on the bottom, it is your left side. So this shear stress, it is on the fluid element, So on the layer of this fluid, any layer, let's suppose this is fluid 1 and this is fluid 2, and there are the separation of this layer. So on that layer, the stress which is in this direction. So this is the stress on this layer. Okay. So to balance this one, the bottom layer of bottom portion, the stress is in this direction. Now, so if this bottom layer, the stresses in a left side direction, so on this fluid element, this is in right side direction. Very good. This is in right side direction. On this fluid element, it is in right side direction. It is in right side direction. Okay. If on this fluid, the right side direction, the stresses on the bottom one, it is in left side. So if the stresses on the bottom fluid, bottom portion, it is in left side. So on the bottom surface, it is in right side. Clear? That means if you take any imaginary layer, on that layer, the stress value, this is what, beta? This is what? tau, this is tau. Which direction? Y direction. Which direction force is applied? X. This is the shear stress on this imaginary on top side. What is the shear stress here? Tau yx. And this tau yx and this tau yx make a shear. And these two values are same. Why? Because this is action, so this is a reaction. Yeah, this is a reaction, so this is an action. So this tau yx on the top and tau yx on the bottom are same. It is not changing. These are the very good boundary condition, I am telling you. Now, someone asks you in this case, someone asks you in the interview, someone asks you, my dear, ki beta, what is the direction of the stress on the top plate? What is the direction? What is the direction on the top plate? So the direction on the top plate, the shear stress direction on the top plate is your left side. What is the direction of the shear stress on the bottom plate? What is the direction on the bottom plate? If it is left side, so it is a right side. See, it is your right side. So this 2-1 is a shear stress acting on the wall due to the fluid, and this one and this one are the positive shear stress. Yes. Why? Because it will be clockwise. It will be clockwise. So see, it will be give clockwise on the fluid element. This one and this one, this one and this one creates a clockwise moment. So these are the positive shear stress acting on the fluid element next to the wall, next to the wall. So on the fluid element, it is in right side direction on the top of this one, bottom of this one, it is in left side direction. It will produce a positive. Now, so for that one, if you understand, for that one, what is the important boundary condition? This is very important, I am telling you. That is, what is the important boundary condition? First one is no slip. First condition is no slip. That means both fluid. That means if the fluid at here, let's suppose the fluid at this point and fluid at this point. Okay, fluid on this point and fluid particle on this point. So both of the fluid have the same velocity. So on the layer, at this layer, the top fluid on this layer and bottom fluid on this layer have a same velocity. Why? Because there is a no slip boundary condition. That means this fluid particle will stick on this imaginary layer, yeah, real any layer, and this fluid particle will stick to this layer. And if you drag this layer, both particle velocity are same. This is the first boundary condition. I am telling you, very important. Now, the second one is that stresses acting. This is very important. Stresses acting a fluid interface. Let's suppose this is your interface is continuous. Yes. Why? Because it is not discontinuous. It is continuous. Why? Because what is the shear stress at the at the layer of top layer, and what is the shear stress of the bottom layer? These are continuous, and since the shear stress is a constant in the fluid, yes. Why? Because this is a caught motion. So shear stress is constant. Yes. At the interface, the shear stress is continuous. Shear stress is continuous. There is no any discontinuity, and we know that shear stress is a constant value in the caught flow. With why? Because what is the shear stress? Mu v by y. Mu v by y. V is the velocity of this one, and v by h, and h is the gap. So what is the stress? Stress tau yx is equal to mu v by h, and this is your constant. This is your constant. So what is the shear stress on this layer and what is the shear stress on this layer are same, and since the shear stress throughout is constant, that means shear stress are constant in the fluid, so the shear stresses on the plate should be identical. That means what is the shear stress on this plate and what is the shear stress on this plate, both are identical. That means if you take this shear stress tau yx top, and if you take this shear stress tau yx of bottom, both if you take the ratio tau yx on the top and tau Yx on the bottom plate, what is the ratio? 1. Without any calculation, you can say that it is 1. Clear? That condition is clear? If it is clear, then we have to go to the very good things for that one. What is that? Please see. Please see, my dear. If you have any confusion till now, I am very happy to reply you. Is there any confusion? Any confusion regarding this one? Please, is there any confusion regarding this one? I am very happy to explain it. Okay. Now, so these are the direction. Now, my dear, let's try some problem. Before I start some problem, I will discuss something. What is that? Please see. If the fluid is flowing due to the displacement of a boundary only, the velocity profile is linear. But if the fluid will flow due to the pressure difference, the velocity profile is not linear. It may be parabolic or other than that. If the fluid flow with uniform velocity, the shear stress is 0. There is no any shear stress. That means, see this one. If someone says that, ki beta, let's suppose this is your chunk of the fluid. Let's suppose this is your chunk of the fluid, my dear. Let's suppose this is a chunk of the fluid. Okay. This is a chunk of the fluid. Okay. This is a chunk of the fluid, and this all the fluid. This is if you take a coordinate. If you take with a coordinate. If you take the coordinate. This is your y-axis. This is your x-axis. Okay, this is your x-axis. This is your x-axis. One second. This is your x-axis, and this is your y-axis. Okay, my dear. Now the fluid is flowing with this one is a uniform velocity. That means all the fluid velocity component in x direction is constant. Same. That means what is the fluid will flow here? Same velocity. Here same velocity. Here same velocity. All the fluid, and when it is possible? When it is possible, beta? Please tell me when it is possible. When it is possible, in which condition it is possible? When this fluid is not contact with any solid boundary, not contact any. This fluid will be free flow. That means what is mean by a free flow? That means the fluid will not any contact with the solid surface like a fluid is flowing. Okay, so this all the velocity is constant. That means this is called uniform velocity. This is called beta uniform velocity. That means all the layer. That means all the layer of the fluid have same velocity. Same velocity. Now, my dear, so this all the same velocity. So if the velocity is the same, that means there is no any gradient. So at any point of dy, the change in velocity is 0. That means in this case, the slope du in x direction, variation in y direction divided by at any y is equal to 0. Yes, yes or not? Yes or not? Yes or not? Okay. Now, if you apply the shear stress tau yx is equal to mu into dux over dy, this dux over dy is 0. That means shear stress yx at any layer is 0. That means in this case, the shear stress is 0. That means there is no any shear stress. This shear stress is all 0. That means what is the shear? There is no any induced of the shear stress. So uniform flow have a 0 shear stress. So if there is a 0 shear stress, we cannot say that this is a viscous fluid. So these are the inviscid fluid. These are the inviscid. Why? Because there is no any momentum transfer. So this is your viscous fluid, inviscid fluid. Inviscid fluid. My dear, in viscid fluid, it is not like that the viscosity is 0. No, viscosity is present, but there is no any messenger. That means fluid don't know if I have a viscosity or not. That means the gradient is 0. That means this gradient is parallel to, this is a velocity profile. This is a velocity profile. This velocity profile parallel to the y direction. So the gradient is 0. So the shear stress is 0. So in this case, there is no any shear stress. But if we take the possible flow, that means it is like that. There is a pipe. There is a pipe, my dear. This is a pipe, a plate. Let's suppose this is a fixed plate. And this is also fixed plate. And we want that fluid is flow. How fluid is flowing? How the fluid will flow? Due to the pressure difference. Hi Atul. Hi. Due to the pressure difference. So let's suppose you have to take any cross section. This is your upstream and downstream. There must be a pressure gradient. That means the pressure will differ. So here let's suppose pressure high, you can write like that. One second, my dear. Let's suppose this is like that. We have to make some good arrangement. Let's suppose, what is that? There is any channel, any pipe. You may ask anything, my dear. It's my humble request. Anyone who are watching the video, I won't say that. Please ask some question. Okay? Inviscid flow and inviscid fluid. Yes. Differ. Inviscid flow and inviscid. See, inviscid is what? Inviscid is what? What is mean by inviscid? There is no any shear stress. If there is no any shear stress, that means there is no tangential, but still it is flowing. Still it is, that means there is no any messenger, there is no any momentum diffusion. So inviscid flow and inviscid fluid have a two different. Inviscid flow, that means there is no any messenger, there is no any momentum diffusion. And inviscid fluid, that means the fluid have a no induced viscosity. Why? Because beta, viscosity, your question is good for the interview purpose. See, viscosity, one second, viscosity, please tell me, is a fluid property or flow property? Viscosity is a fluid property or flow property? Viscosity is what? Fluid property. Okay. Fluid property. Okay. This is your fluid property. Now, this is present or not present. Who decide? This is present, yani this will be induced or not. Who decide? Flow property. Flow properties. Yes. In the fluid, it will be present. That means it gives the action or not. Who decide? Flow property. That means, see my dear, here is the flow. Here is the flow, but still there is a viscosity. Yes, there is a viscosity. So that is called inviscid fluid. That means there must be inviscid fluid. That means inviscid, here it is, inviscid fluid, you can loosely say that inviscid flow. You can say that. So inviscid flow, that means inviscid flow, that means the shear stress is 0. Inviscid flow, that means the shear stress is 0. Why? Because shear stress is the momentum flux, it is 0. So inviscid flow that means tau yx is 0, that is fixed, and in viscid fluid, that means mu have no any role, have no any, mu have no any role. Clear? Clear? In viscid flow, that means shear stress 0. In viscid fluid, that means mu have no any role, and both are the synonyms. That means they have a no any role. Why? Because there is a no any momentum flux. If there is a no any momentum flux, that means no any messenger, viscosity is not present, but the viscosity have no any role. So if there is a container of water and that water is erased, we cannot define the viscosity. That means we cannot define the viscosity, also we cannot define the momentum. Why? Because if you not define the viscosity, you cannot define the momentum diffusion. So in viscid flow, so your answer is, conclusion of that, in viscid flow and in viscid fluid is different. Clear? 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 I hope clear. Okay? Now, think that if there is any channel and there is a pressure difference, this is a pressure high and there is a pressure low, so if you take any cross section, there must be this velocity profile like a parabolic. So in this parabolic velocity profile, beta, this is Poisson flow. In this parabolic profile, this point the velocity is 0, this point the velocity is 0, and this point is velocity is maximum. So in this case, shear stress will vary. Each and every layer, the shear stress will vary. Where is the maximum shear? The maximum shear, it is in top plate, and the minimum shear, it is in center of the pipe, a plate. So shear stress, it is vary. Here the shear stress is 0. In this case, shear stress is constant. In this case, shear stress constant. So while the fluid is flowing, you cannot say that sir, shear stress is 0, shear stress is constant, shear stress is varying. If you understand under which mechanism the fluid will be ignited, flow will be ignited, under boundary displacement, either pressure difference or combined of these two, accordingly you can decide shear stress is what is the shear stress. See my dear, who is the responsible of this flow? Who is the responsible of this flow? This flow is responsible due to the pressure. The fluid is flowing. How it is really flowing? Due to the pressure. That means at that point high pressure, that point low pressure. But still it is all the layer have a uniform velocity. Why? Why? Because there is no any solid surface. So still there is a pressure difference. High pressure, this is high pressure layer, this is low pressure layer. So high pressure, low pressure, it is not practical, it is like bulging like that. That means this is high, just hammer it. This is low, so it will bulging like that. This is. So it is an ideal case. That's why this is called ideal flow. This is called ideal flow also. Ideal flow. So in the case of ideal flow, there is no shear stress. In the case of this flow between the two parallel plate, flow within the plate, the viscous shear stresses differ, and flow between the two parallel plate, one plate moving with the constant velocity without any pressure difference, the shear stress is constant throughout. Clear? Clear, my dear? Now, so we have to start this problem first of this problem. This is a very important problem. This gives the many consequence. What is that? Please see this question, beta. This question is that determine the magnitude and the direction of the shear stress. Determine the magnitude and the direction of the shear stress that water apply. That means what is our system? Water will be applied. That means water will be applied to the base and to the free surface. So we have to find the shear stress that water will be applied to the base and to the free surface. Find the shear stress and also direction. These are any fluid is flowing and that fluid is a free surface. That means in this it will flow. How it will flow? It will flow due to the gravity effect. It will flow due to gravity effect. This is the gravity effect. Okay, so it will be flowing like that. Okay, now if it will be flow, this is your velocity profile. It is given. This is your velocity profile. It is given, my dear. This is the velocity profile. It is given. Okay, what is this one? Please tell me. This is the velocity, any parabolic. Why? Because y square. Y it is the direction perpendicular and this is the direction along the flow. These are the water like a river. It is like a river. Now my dear, this u it is in x direction. This u it is in x direction. Variation along y direction, that is equal to capital U into 2 y by h minus y by h का whole square. Okay. Now this is your velocity profile. Once you have a velocity profile, very easy to calculate the shear stress. What is the shear stress? The shear stress variation, it is in y direction. It is in, my dear, y direction. It is in y direction. That means tau yx is equal to mu du over dy. Okay, du over dy. Now you have to differentiate it. Easily you have to differentiate it, put the value and shear stress. But we have to think the direction also. So, my dear, if you differentiate this one, dy, what is the value? This u is outside. 2 by h minus 2y by h. Yes or not? This is okay? Now, if this is okay, then just put this value back. Just put this value back to into, okay, differentiate it, y with respect to y. So, here 2y and h square is there. This is h square. 2y h square. Okay, correct. 2y h square into u by h. Okay, so this is, so if you put this value here back, so this is mu u by h, yes or not? Mu u by h, also you have to take 2 into 2 by 1 minus y by h. Y by h. Yes or not? This is shear stress. This is shear stress. Now, my dear, if you are finding the free surface, so free surface tau yx at free surface, that means at y is equal to h, put y is equal to h, this is tau yx at free surface, that is 0. This is very important boundary condition. This is very important boundary condition I am telling you. That means at what is the consequence of the free surface? The consequence of the free surface that there is no any tangential force. That is the consequence of the free surface and it is proved. Now, at the base, if you put this at the base, that means h is equal to 0, y is equal to 0, that is your this one. So, at the base, this is your y equal to h. So, this is your 2 mu u by h. That means at the base there is a maximum shear stress and at the free surface there is a 0 shear stress. Clear? What is that? they are asking that, so this is the stresses. Now they are asking that what is the direction that water apply? This water will apply on the free surface or on the plate. See my dear, think this. So these are the velocity profile. You have this one. At the base, this is your, at the base 2 mu u by h. That means this is the stress the wall exerts. The wall exerts on the fluid. The fluid will exert on equal but opposite stress on the wall. Yes. See, this is your fluid element. This is on the wall. This is your fluid element. This is your fluid element. So they are asking that the stresses water that apply. So water apply on the wall, that means you have to find the stresses applied by the water on the wall and stresses applied by the water on the free surface. So my dear, what is your answer? Direction. What is your answer? So this is your water. So water will try to flow in a right side direction. So on the wall, see, water will flow in this direction. So this is your what? This is the stresses exerts on the fluid. On the fluid it will exert. The fluid will exert equal but opposite stress on the wall. So this fluid element is try to move in this direction. In this direction. So on this fluid element, this is let's suppose this is a fluid element and this fluid element faster. So this fluid will try to exert this in this direction and this fluid element will try to exert in this direction. So these are the stresses. These are the stresses act by the wall on the fluid. So this one is, that means this is your wall and this is your fluid element. This is your fluid element. So on this fluid element, there in this direction there is a motion. There is a motion. So on this fluid element, this direction the shear force stress is applied. Due to the Newton's third law, on the wall, this direction the shear stress applied. On the wall. So this is in this direction. So on the wall, by the fluid, right side. On the wall, so on the wall, by the fluid, by the water, on the base, it is right side. Right side. Clear? Which direction? Right side. So on the wall, this is the stresses on the wall. This is your tau wall. Tau wall. Stress will act on the wall. Now, what is the direction of the stress on the free surface? Please tell me in the reply comment box. What is the direction of the free surface shear stress? What is the direction of shear stress to the free surface? Please tell me. Please tell me what is the direction? We cannot define. Why? Because the shear stress at the free surface tau yx is 0. So we cannot define the shear stress direction at the free surface. So someone asks you, frequently ask you, my dear, what is the direction of the shear stress at the free surface? What is the direction of the shear stress of the free surface? अरे भाई, shear stress itself 0. So कैसे आप define कर सकते हो direction? So there is no any direction. So on this one, if you taking the fluid element, if you take the fluid element, my dear, right side. If you take the fluid element, very important, I am telling you. So at this surface, so this is a fluid element, and this fluid element will want to move. So in this one, it will act in this direction. So this is your viscous shear on the fluid element at the free surface, but at the free surface here it is 0. This is 0. This is 0. Now my dear, now who is balanced this shear stress? Who is balance? Please tell me. Who is balance this? This is the element at the free surface. At the free surface, shear stress 0, and this who is the balance of this? Why? Because if you take a free body diagram, this element whose balance this force? This is, let's suppose, viscous shear stress F, and this F is 0. This F is 0. So whose force is balance this force? Please tell me. Whose? It may be pressure. It may be pressure. Why? Because this is horizontal. This is your horizontal. So in this direction, there is a high pressure. In this direction, that means P plus delta P. In this direction, there is a low pressure P. So this pressure difference is balanced by this force. Clear? 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 I am telling you. This is clear or not? Okay. So what is the consequence of that one? The consequence of that, the fluid element adjacent to the wall with a positive tau x as shown. Fluid element adjacent to the wall with fluid element with the positive tau x. So this is your positive value. So on this wall, this in this direction, the wall on that wall, this is your tau wall. Tau wall. Clear, beta? Now, at the free surface, shear stress 0, that means, very important, that means air at the free surface. In this one, what is that with here? Air. So what is that? Air at the free surface does not exert any stress. Very important. Why? Because already air have a very low viscosity. Very low viscosity as compared to water. On the water, although in the reality, the air will be exerts a small shear stress. In the practically, very small shear stress on the water, assuming that the shear stress is negligible in the reasonable in the most of the engineering application. So here practically there is a shear stress act by the free surface, act by the air, but that shear stress is negligible, and it will prove. It is proven. So at the free surface, the shear stress, that means the tangential force in this direction, tangential force is 0. But still the tangential force is 0. How the fluid is flowing? The fluid is flowing due to the pressure difference. This is high pressure. If there is a horizontal, this is your high pressure, and this is your low pressure zone, low pressure. That's why the fluid is flowing. Yeah, either it will be tilted. So gravity, it will be like that also. This your bed is there, and this is your fluid is flowing. So it may be like that. So this is the due to the gravity. What is that? Gravity effect. G. G is there in this direction. G. So this is flow, and this flow is due to the gravity effect. So due to the gravity, it will flow. So in this condition, the fluid is flowing. But what is the, if you take the element of this fluid element, if you take this element on the fluid element, this is the force equation. So this force will be balanced by the pressure difference. I am telling you, someone ask you what is the mechanism at the free surface. Clear? Now next problem we have to solve this. Yes, this is your problem. Simple thing. Simple problem is there. Okay, see, no slip condition. What is the state that no slip condition? That means stick to the solid surface. Two immiscible layer. There is a two immiscible layer. On the Newtonian fluid are dragged along the motion of the upper plate as shown in the figure. The bottom plate is stationary and the velocity profile of each of the linear velocity profile. That means there is a fluid is flowing due to the displacement of a boundary. The top fluid, this is top fluid 1, have a specific gravity 0.8, kinematic viscosity 1 centistoke, puts a shear stress on the upper plate, and the lower fluid 2, a specific gravity 1.1, kinematic viscosity 1.3 centistoke, puts a shear stress on the bottom plate. Determine the ratio. See the beauty. What is your option? Please tell me. What is your option? Option number A. I will give the option. Option number A 3.8, option number B 2.1, option number C 1, option number D none of these. What is your option? Please tell me. What's your option? Who are watching this video, please tell me what's your option. This is 2.1. This is 3.1. What is the option, beta? What's your option? Please tell me. Without any calculation, this is 1. See the beauty. Why? Because these are the constant shear stress. Why? Because in this case, there is no any pressure. The shear stress throughout constant. So what is the shear stress on this plate? The same as shear stress on this plate. So if you take the ratio, that is 1. Without any calculation. I am telling you, many students get afraid. Ki, sir, this is a very good question, and no, this is very faltu question. Why faltu? Why? Because once you have to understand the concept of the stress boundary condition, very easy to handle this problem. Very easy. Without any calculation, you can prove it also. You can also prove it, no problem. Without any calculation, you can take 1. Why? Because the shear stress is very constant. This is the category of a chord flow with no pressure gradient. The shear stress is constant. So shear is constant, the shear stress on the top and the shear stress on the bottom is same. So the ratio is 1. Clear? Clear, my dear? This is clear now? So if this is your imaginary layer, I will just discuss the one mechanism here. If this is your imaginary layer, my dear, this is your, let's suppose this is your layer. On this layer, my dear, on this layer, see, if this is a fluid element, let's suppose this is our one fluid element, these are the another fluid element. Okay, these are, please define the direction, See, plate will move in the right direction, okay, plate will move in the right side direction. So on the plate, in this direction, shear stress will applied. This is a shear stress applied on the plate by the fluid element. On the fluid element, in this direction, the shear stress will apply. Okay. So the lower portion in this direction, okay. Now this layer have also motion. This layer have a motion, my dear. This layer have a motion. Yes or not? How much velocity? This is your velocity. Let's suppose this velocity is Vi. Let's suppose this velocity, this is your velocity, it is given. What is the velocity? 2 meters per second. So let's suppose this is your Vi. Intermediate. What? Okay. So if this is a Vi and this is, so the shear stress on this Vi, top plate, it is hit in this direction. In the bottom layer, it is in this direction. It is visible? Yes. Now, on the top layer, it is in this direction. On the bottom layer, it is in this direction. So at the plate, it is in this direction. Clear, my dear? This is the shear stress direction. It is visible, na? It is visible or not? 1 second, I will check. It is visible or not? Please tell me. Yes, it is visible. No problem. I will just change that color. This is in this direction. This is shear stress on the fluid. This is shear stress on the fluid element. This is the shear stress on the fluid element. This is the shear stress on the fluid element. Okay. And this is the interface. This shear stress at the interface. So at the interface, let's suppose this is our interface. Let's suppose this is our interface. This is our interface. So at the interface is moving. Very great. This interface, it is moving like that. This interface, it is moving. This is your motion. Thank you, Sandeep. This is moving. Now on this interface, in this direction there is a shear stress of the top, and this direction, the bottom, it is the shear stress. What is this? This is tau yx, and this is tau yx, and this will be positive, and my dear, and this tau x due to the top and this tau x due to the bottom is same. That means the ratio is 1. So if you take any layer of within the fluid, and that is for the caught flow, why? Because the shear stress is constant. So if you take any layer, so just immediate to the that means the shear stress due to the top and shear stress due to bottom is fixed. That means in this is for fluid 1 and this is for the fluid 2. So tau yx for the fluid 1 divided by tau yx for the fluid 2 is 1. Without any calculation you can check. Velocity is continuous, but velocity is, see, very good. See, yes. See, this is the velocity, and it is not a continuous. Why? Because see, velocity is not a continuous. Shear stress continuous. Atul, sir, in this case, velocity is continuous. No continuous. Why continuous velocity? See, velocity is not continuous. Why? Because beta, this have a, if there is a same fluid, one second, Atul, one second. If there is a same fluid, then the velocity is continuous. But here is the different fluid, that means the different viscosity, velocity is not continuous. Why? Because this have a different velocity, this have a different velocity. So both have a different velocity. Viscosity. This have a viscosity, this have a viscosity. That means, sir, all the layers have a different velocity, then how shear stress is called? Yes, sir. It is all the layer have a same velocity, the shear stress is 0. It is not a meaning of a constant. All the layer have a same velocity, shear stress is 0. It is not a question of constant or variable. But if there is no any pressurized, only displacement of a boundary, there is no any pressure difference here. So in this case, shear stress is constant. Yes, already we have to prove it. See this one. Yes, this is the layer. So velocities differ. Atul, velocities differ. Yes, velocity is varying. Though there is a velocity is varying, but the shear stress is constant. See, mu V by H. Mu is constant, V is constant, H is constant. So shear stress is constant each and every layer. बसरते क्या होना चाहिए? Pressure gradient 0. If there is a pressure gradient, you cannot say. Clear? So it is not like that, sir, all the layer have a different velocity. So how can you say that? No, that is the bad concept. Okay, it is not like that. See, one thing is very important here, understood for the fluid mechanics. Shear velocity field have a own characteristic and shear stress have a own characteristic. It is not like that. See, my dear, if their velocity is constant, gradient is 0. If the gradient is 0, shear stress is 0. So if the all layer have a same velocity, there is no any meaning of the shear stress. Shear stress 0, like a free surface. At the free surface, there is no any shear stress. See, at the free surface, there is no any shear stress, my dear. See, at the free surface, there is no any shear stress. But you cannot say that, sir, the velocity is 0 or what? There is a velocity, but we don't know what is the velocity. We can find it. What is the free surface velocity? You can find it. No problem. But the shear stress is still 0. So shear stress is still 0. That means if you draw the velocity profile further. So if you draw the velocity profile further, you can draw like that. Understood? But this velocity profile is due to the air. and this velocity profile due to the water. But what is the velocity profile? This is the velocity profile. Why? Because all the layer have the same velocity. All the layer, so that free surface not called interface. Interface, free surface, both are the different thing. At interface, shear stress are same. At interface, shear stress are same. Okay, but at the free surface, shear stress is 0. Only the force will act as a normal force. Clear? So, free surface you cannot call it is an interface. No. Interface, that means interface, see, you take any interface. If you take any interface, the shear stress are varying. That shear stress are constant. See, if there is an interface. So, what is the shear stress? This one and this one. These are same. These are same, but this is or agar if there is shear stress is varying, let's suppose it is like that. Okay, it is like that. Let's suppose there is a parabolic. I will again clear. This is a parabolic. Okay, you take only one layer, this layer. So my dear, if you take this shear stress at this one and this shear stress at this one, still these are same. At interface, the shear stress are same. Yes, please mind it. At interface, shear stress are same, but that shear stress is not throughout same over the cross section. Why? Because velocity profile is parabolic. That means, see, if let's suppose it is a velocity profile. This is first velocity profile. This is second velocity profile. Clear? This is third velocity profile. Okay? 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 3 velocity profile is there. Okay? So, these all in, see, case number first, case number second. This you have to disregard, cut it first. This one, the velocity is differ. All the layer have a different velocity, all the layer have a different velocity. Clear? This is moving by the displacement of a boundary, and this is your high pressure, high, and this is your low pressure, and there is a motion. Okay? Now, if in this one, the velocity profile is linear. That means this is a constant velocity. This will move a constant velocity. That means this is a linear. Now, in this case, if you take any layer, so in this layer also there is shear stress. Yes. If you take this layer, if you take any layer, yes, it is also a shear stress. Yes, it is also shear stress, number first. But let's suppose this is tau yx, this is tau yx, this is tau yx, this is tau yx. This tau yx above that one and below that one are same. Very important. 1, let's suppose this is 0.1 and this is 0.2. Tau yx 2. This is same. In this case also same. In this case also same. At this layer. Why? Because at this layer, what is the velocity top and velocity bottom are same. So same shear stress. But this shear stress not throughout constant. But this shear stress throughout constant. That means if there is a upper plate is there and there is a lower plate is there, so this shear stress same. So this is another boundary. This is the separate boundary condition. What is the boundary condition? At the interface, the shear stress are continuous. That is a very important. See, at the interface. See here. At the interface. See. At the interface. One second. Yes. At the interface, shear stress are constant. Continuous shear stress. See. at the, see, stresses across the fluid interface. This is very important line, I'm telling you. This is very important. That's why I'm discussing regularly, continuously. Why? Because many students get confused here. See, stresses across the fluid element, fluid interface is constant. That is very important thing. Constant. Now take this case. Since the shear stress is constant in the fluid, in a caught fluid, no pressure, so the shear stress ratio on the plate top and bottom are identical. So these term are differ and this term are differ. So say if you take any interface, either the linear velocity profile or either the parabolic velocity profile, if you take any interface, the shear stress is constant. That is fixed. Shear stress is constant, but that shear stress is throughout constant or not, that will depend upon your engineering model. What type of model you have to select. So you have to take a model due to the boundary displacement. So shear stress, each and every layer are same. So the ratio is 1. Clear na? Clear na? This is clear or not? Please tell me. This is clear or not? Please tell me. So, sir, all the layers having a different velocity, then how shear stress comes in? Thank you very much. So that is the things. So we have to left one problem here, no problem. Just you have to solve this problem. This again the problem of a boundary condition. So these are the boundary condition and this also. So what is the motive of this class? Previous and today's class, just we have to clear about the boundary condition. Okay, that boundary condition, one questions damn sure will ask in the continuous gate examination. So in this one there also a boundary condition is there. Okay, so my dear, please try to solve, take a snapshot and try to solve this problem. Okay, the velocity profile it is given, there is a cylindrical, there is a thin. This will be helpful while you have to design the component again. Free conduction. This is your convection, free convection effect. That means this is your film condensation. This is your film condensation. There is a film is there. So this is a film condensation. It's any surface is there. So if there is this rod have a temperature equal to the saturation temperature of the vapor, so it will be condensed and it will be tried to a film. That means if this is your cylinder, so there is a condensation and this condensation will be creates a layer on that one. So this layer, how to define a force balance, that is a very important thing. This is very, you don't teach fluid mechanics only like a fluid. You learn fluid mechanics don't like a fluid. You learn a fluid mechanics like a mechanics. That word is very important. Don't learn fluid mechanics as a fluid. Learn fluid mechanics as a mechanics. That gives the extra feel of the fluid mechanics. Thank you. Bye-bye.